This is an introductory video about fluid mechanics. What you should know is that fluid mechanics is difficult. The concepts are difficult to grasp if you have never heard of it or if you've never had any experience with it. If you're dealing with fluid mechanics for the first time, then yeah, it's going to be difficult. You're going to be coming across new concepts, new equations, complex equations, but as long as your basis in physics and mathematics is good enough, you'll be able to glide through fluid mechanics and any courses related to that. Some of the equations you may have already heard about, like Bernoulli's equation, or Newton's second law, or ideal gas law. And then there's going to be a lot more equations that you're going to be coming across for the first time. Just to introduce you and relate fluid mechanics to solid mechanics, if you've studied concepts from solid mechanics before, so then you would know that the mechanics of solids is divided into two types. You've got statics, which is basically you dealing with bodies at rest, and you've got dynamics, which is when you're dealing with bodies in motion. And then dynamics is further subdivided into the kinematics of it and the kinetics of it. So when you're talking about kinematics, you're dealing with the body itself. You're not looking at the forces that are interacting with the body. And when you're looking at the forces that are interacting with the body, that is called kinetics. So just like that, this is mechanics of solids when you're dealing with steel, when you're dealing with aluminum and stuff like that. But just like that, you also got mechanics of fluids. So any kind of fluids, we're going to come to the definition in a bit. You're going to be dealing with the fluid statics when you're dealing with fluids at rest, and then you're dealing with fluid dynamics when you're dealing with fluids that are in motion, that are moving. So these are two ways to classify the mechanics of fluids. And now what I want you to do is I want you to just imagine just for a second kinds of fluids that are in and around you, and just take a moment to think about that what can you classify as a fluid? I mean, whether you're sitting at home, whether you're sitting at work, you're going to have examples around you, loads of examples around you, that if you were to think about them in detail, you would understand how you classify them as fluids. And that is just for you to understand how fluid mechanics is related to your daily life. So the most basic of examples is going to be the blood that is flowing through your human body. So the blood is flowing through the arteries, if it's flowing through the veins, and if you think about it, they can be you could say that they can be modeled, the veins and arteries. If you were to model it, you could model it as a constant diameter pipe in a way, and then you've got blood flowing through them. So that is an example of a fluid flow. Then you've got rainwater, you've got water flowing in a river, and multiple examples as you expand. And so you can go from different scales. You can go from the smaller scales, from micro scales to macro scales. You can talk about the act of pouring water into a glass, tap water through your pipes, air conditioners, or flow past a bike rider, or flow past a car, the flow of air past a car. So you could see how many different kinds of materials are being classified as fluids. You've got blood, you've got water, you've got wind, you've got air. So all of these are classified as fluids, right? So whether you're dealing with small scale applications of it, like tap water through your pipes, or whether you're dealing with the industrial applications of it, like aircraft, propulsion systems, cars, automobiles, power plants. So all of these are examples of fluid flow. So then the question arises that how can we, make that distinction between the solids or the fluids, and what do we usually, classify as a fluid in the first place? So a general idea, if you were to think about a solid, if you really think about it, it's something that is hard. It's something that doesn't deform easily. And just like that, on the opposite end of the spectrum, you've got fluids, and fluids are softer. They deform easily, like when you pour water into a glass, or when you're moving, and the air basically envelops around you. So the air is deforming around your body. It's moving. It's soft. But this is just a casual observation. So if you were to look at it in more detail, you would find that if you were to look at the molecular structure of a solid, then uh, it has these densely spaced molecules, and then they've got these intermolecular forces, and these are really strong forces. So you've got bonds in here that allow the solids to maintain their shapes, and then they're not easily deformed because they're closely packed together, all these molecules. And then if you were to think about water or a liquid or an oil, then you would, uh, from a molecular structural point of view, you would identify then that the forces between the molecules now are going to be smaller than they were for the solids. And the molecules then have more freedom to move. So then liquids can be deformed easily, and they can be poured into or out of a container. And then when you move towards the gases, now the intermolecular forces are even weaker for gases, and the molecules have got even greater spacing between them. So there's more freedom of movement between the molecules. And then as a consequence of that, the gases are more easily deformable. They're compressible as well, and they will completely fill up the volume of any container that you have. So what that tells us is that both liquids and gases are classified as fluids. But this is still a distinction that um, we need to refine even further, because if we were to go with a molecular structural definition for fluids, that is not enough for us as engineers, because as engineers we cannot model every single molecule, because there's tons of molecules even in a small space of volume. So then we need to come up with some other kind of definition through which we can identify what a fluid would be. And that more specific definition from an engineering perspective would be that a fluid is a substance that deforms continuously when it is acted upon by a stress, by a shearing stress to be specific. So just to give you a background on what stresses are, if you were to, let's say, have this material here, whether it's a solid, whether it's a liquid, let's just think that it's a solid, and it's bounded on this side, so this side is fixed, it's not moving, and you were to apply a force in this direction on this area, then this would be basically a normal stress. A normal stress would be generated, because if you're applying the force in this direction, then you would have deformation over here if, let's say, the length of this object, you can identify it by L. Then if you're applying this force, there's going to be some minute small deformation, which you could classify, let's say you could identify as delta L over here. Okay, so the strain is then going to be so you've got the stress, which is defined as force divided by area. And because of that stress, a strain is being generated, and strain is nothing but the deformation that is being generated, which is delta L divided by L, change in length by total length. So just like that, if you had this same solid and you were to apply a force in this direction, in a direction which is parallel to the area, then this will generate a shearing stress, and that is represented by tau. And again, it's going to be force divided by area. Okay, except that the force is in this direction now, in the tangential direction now. So what is going to happen now? What's going to happen is that because this side is fixed, so and I'm just showing you these changes in a way that is visible to you right now. Obviously, when you're applying this kind of force, maybe that deformation is not even visible to the naked eye. But just for a demonstration's sake, let's say that if I was to apply a force in this direction, then what's going to happen is that this solid is going to deform in this direction, okay, and these edges are going to stay at the same place. So this is going to be the deformation. And once I remove that force, this is going to go back into its original shape. Okay. So let's just assume that that's what's happening with a solid. Now, is that same thing going to happen with a fluid? If this was a fluid and you were to apply a force on this, do you think that this fluid is going to deform to a certain extent and then come back to its original shape? That doesn't happen. We know that intuitively as well. That when we apply a force on a fluid, let's say you've got a glass of water that is full of water, and you apply a force in this direction on the glass of water, what is going to happen? The fluid is going to move with your hand, and it's going to flow out of the container. It's going to flow out of the glass. So basically, once the fluid deforms, it deforms continuously, okay? And this continuous deformation is called flow, right? So for a solid, if you were to apply a shearing stress, which is force per unit area, then it's going to deform to a certain extent, but that deformation is not going to be continuous. Once you remove this force, the solid is going to come back to its original position. And if you were to do the same thing for a fluid, there's going to be a continuous deformation. And that is how you can imagine if let's say you had water, or if you had oil, or if you had air, all of those satisfy this definition for a fluid, that they flow when they're acted upon by a shearing stress. Okay, so this is a more comprehensive definition for a fluid, that a fluid is defined as a substance that deforms continuously when acted on by a shearing stress of any magnitude. So now let me come back to that point, that why is this definition not good enough for us as engineers, the molecular structural definition. And to illustrate that, let's imagine that this is one of the molecules of a fluid. Let's say this is a gas or a liquid. It has a certain diameter. And then you've got, if you've got a molecule here, you're going to have another molecule next to it, another molecule next to it, and then there's going to be spacing in the middle as well. So for gases at usual pressures and temperatures, the spacing between, say, the spacing between the molecules is of an order of 10 to the power minus 6 millimeters. This is for gases. And for liquids, the same spacing is of the order of 10 to the power minus 7 millimeters. Another thing that you should imagine here is that if you were to take a certain volume, let's say if you were looking at a 1 cubic millimeter of volume, and so if I was to, let's say, if this is a box, you got 1 millimeter in this direction, 1 millimeter in this direction, and 1 millimeter in this direction. This is going to make up a volume of 1 millimeter cube. In this 1 millimeter cube of volume, the number of molecules of gases you're going to have in here is going to be 10 to the power 18. So can you imagine that the amount or the number of volumes that are the number of molecules that are present in this small volume? It's huge, right? This is the number of molecules present in this volume for gases. Okay. And for liquids, you're going to have about 10 to the power 21 number of molecules in the same amount, in the same volume. So that is a huge number of volumes in a very tiny volume. And that's why you can't really study, or it's not feasible to study fluids on a molecular level, because if you were to do that, then what that means is that you have to find out, for example, the temperature of each volume, the temperature of each molecule, the pressure of each molecule, or let's say the velocity of each molecule, and so on and so forth. So you have to find out all the fluid characteristics for each molecule, and that is why studying fluids on a molecular level doesn't make any sense, because can you imagine that you have to go and find out the information of these fluid characteristics on a molecular level? That's kind of insane, you would imagine. So instead of that, what we do is we use the continuum approach. And what the continuum approach means is that instead of looking at all of these molecules, we take the average values over a certain volume. Okay. So for example, if let's say this were to be a glass of water, okay, or let's say let's look at a pipe. Okay, maybe it's going to be better that way. Let's look at a pipe. You've got fluid flowing through this pipe. So you've got this fluid has a certain velocity closer to the pipe edge. It has a certain velocity in the middle of the pipe. It has a certain velocity again at this side of the wall of the pipe. And then obviously there's some kind of velocity that is between this center of the pipe and the wall of the pipe, right? So instead of now looking at all the molecules, let's say in this layer of the fluid, we're just taking the average value of all of those molecules, and that is what the continuum approach is. So that makes our lives easier. And now in this way, we found out the velocity information across this pipe, the velocity variation across this pipe. And this velocity variation is also called the velocity profile. So we assume that all fluid characteristics vary continuously throughout the fluid, and we can take the average values over a volume. Okay, that is what the continuum approach is, and how it using this continuum approach helps us in studying fluids. Now I'm going to move on and talk a little bit about the dimensions that we use in fluid mechanics and the units that we use. So fluid and its characteristics, we need to describe them both in terms of qualitatively, which means that we need to define the type of characteristics. So what the characteristic is, for example, what's the length or the time, the velocity, and so on and so forth. And then we also need to give it a numerical value, right? So what is the velocity? It could be, now only a numeral value is not enough, because a velocity of 5 doesn't make any sense. It also needs to have a standard alongside it, so it would be 5 meters per second. Okay, that's your velocity. So you've got the standard and the number that's going to define your fluid characteristic quantitatively. Another approach that we use to identify fluid characteristics is based in primary quantities, and the primary quantities are M, which stands for mass. Okay, M stands for mass. The L here stands for length. The T here stands for time. Okay, this stands for time. Don't confuse this with temperature. When we talk about primary quantities, the temperature is usually represented by theta. So if you were to represent temperature, it's going to be represented by theta. And now, how can we use this? Let's just identify some examples. So if you were to look at area, what is area? It's length into width, and both of them can be identified as lengths, right? So area is going to be, in terms of primary quantities, it's going to be length squared. Okay. The velocity in terms of primary quantities is going to be what? It's what is velocity, right? We have to think about it in terms of the equation. So it's distance by time, which means it's length by time, right? So it's going to be L by T. Okay. And then you could also do it for density. So what is density? It's units in SI units. It's kilogram per meter cube. So kilogram is what? Kilogram is mass, right? So it's going to be M. And kilogram per meter cube. Meter cube is what? It's length. So it's going to be M divided by L cube. Okay, because we're looking at the primary quantities right now. And when we're talking about primary quantities, this is how we use the sign for defining how a, let's say, characteristic is going to be equal to the primary quantities. You could do it for yourselves. Try it for these three different terms. And what's the purpose of this? You could ask, what's the purpose of defining the fluid characteristics in terms of primary quantities? Well, this helps us, and this is going to help us in the future. In the future videos, we're going to see this, that because of defining dimensions by using these physical quantities, we can go ahead and look at any equation, and we can analyze that equation and find out that that equation is dimensionally consistent. So if you were to, for example, look at one of the very basic equations which you look at for velocity of a uniformly accelerated body, which is velocity is equal to the initial velocity plus AT. And A over here represents the acceleration and T represents time. So if you were to look at the left side of the equation, it's going to be L by T, or LT to the power minus 1. And the right hand side of the equation has to be the same as that on the left side, right? So it's going to be, this is going to be the same, LT to the power minus 1 plus acceleration is what? Length, meter per second squared. So it's going to be LT to the power minus 2. And time is what? It's T. So it's, once this cancels out, minus 2 cancels out, and it's going to be the same. So this equation is then dimensionally consistent. Okay. And what this tells us is that all theoretically derived equations are dimensionally consistent. And what that means is that the dimensions on the left-hand side of the equation must be the same as those on the right-hand side of the equation. And all terms that are adding up must have the same dimension as well. Okay? This is the fundamental premise that all equations that we look at that are derived have to be consistent with. Otherwise, we're just going to be adding up different quantities that are not like for like. We're going to be adding apples and oranges, kind of. So that doesn't really make any sense. Okay, so that's why, just to check that, we use these primary quantities to do that, to give us that qualitative and quantitative description of it. Obviously, we can also look at the SI units. Okay, which we usually look at, and that's meters, um, meter second, meter for mass, sorry, meter for length, kilogram for mass, second for time. Okay, so you're also going to be looking at the SI units as well.